So anyway, yeah, my name's Eric Pacuit. This is joint work with Wes Holliday and Alexander Kristoffersen, who is a master's student at Berkeley. Wes is a professor at Berkeley. And what we're interested in is studying the problem of strategic voting. So how do you manipulate the outcome of an election? Okay, and we're using machine learning, and I'll explain how we use machine learning to study this question. So here's the classic setup on how to manipulate. You have 5 voters here. We use Borda. We see the Borda winner here is B. It turns out that the first voter, V1, could submit a different ranking of their candidates. And that would result in an outcome CD. And arguably, that might be better for voter 1. Okay, so the question that you have as a strategic voter is which ranking should I actually submit? So you have the profile, and I want to know which ranking should I actually submit. Okay, now we need to make the job a little bit easier on ourselves because it's actually not 100% clear that CD, the set CD, is actually better than getting B for sure if you look at voter 1's actual ranking. Okay, so to make our job just a little bit easier, we're going to assume that the voters have utilities. Okay, and really all we need is the utility of a single voter, of the first voter, the manipulator. Okay, so the manipulator, so each voter here, we have a set of utilities for the voters, and that gives us the rankings of the alternatives. Okay, now we're going to measure the profitability of a manipulation in kind of a way you probably all would guess. So given the profile where everybody submits their true ranking, their quote unquote actual ranking, and this right here is the profile where one voter or manipulator votes differently. They give a different ranking of their alternatives. And what we're going to look at is the expected utility for voter I of the winning set under this when they actually manipulate the election. Okay, and then we can measure for a particular voting method. So now you have a fixed voting method. What we want to look at is the profitability, the sort of average profitability of a voter manipulating. So that's profitability for a particular voter. Okay, and essentially this is just applying the standard sort of relative utilitarianism normalization. Okay, so we're going to look at the expected utility of the winning set under the manipulation minus the expected utility if I had not manipulated. And then I'm going to normalize this by just looking at the biggest utility I could get minus the smallest utility I could get. Okay, so this is a way of measuring the profitability of a manipulation for a particular voting method. Okay, now here's the sort of key idea that we're looking at. In the usual setting, you have a voter and you have the profile, and the voter is sort of meant to know how everybody is actually voting in that election. What we really want to look at is you're not going to have such perfect information. You're going to have limited information. And so the type of limited information you might have would be something like the plurality scores. So how many first place votes each of the candidates get. Or you might get the, okay, so now the thing is, if you're given the plurality scores, then you don't know what profile you're in, but you have a, there's going to be a whole bunch of profiles that might generate those same plurality scores, and then you're going to want to pick a ranking that sort of is a best response to what you expect the profile is going to be. The other type of data you might have is more qualitative information, like a ranking of the plurality scores. You might get the sincere winners. So you might get so think of this as kind of polling information. So the polling information says, this is who the winner is under the current voting method, okay? Or you might get a little bit more sophisticated information like the majority matrix. So the majority matrix just says for the pairwise comparisons, is one candidate majority preferred to another candidate? You might get the margin matrix, where you not only get this majority comparison information, but actually the margin of victory. And then finally, a bit more qualitative information. So you have the majority relation, but you actually have an ordering over the edges rather than just simply the margin of victory. Okay, so you have all different types of limited information you can get as a voter about the profile. Okay, so what we did is we looked at a bunch of, we thought about training a bunch of neural nets to try to learn how to manipulate a particular voting method. So you have a voting method, you have the utility, so the neural net has access to the utility, and then you have some limited information about that particular profile. And then you want to respond and say, this is the best ranking to respond. You want to try to maximize your average expected profitability. Okay, so that's the basic idea. They're essentially trying to figure out what is this ideal function that, given my utility, will tell me what ranking to submit given this limited information about the profile. Okay. Yeah, and so well, let me say a little. Let me just jump ahead. So we looked at. So obviously, this is going to depend a lot on the probability distribution you're using to generate the utilities. So we looked at 3 utility models, the random utility model. This is sort of kind of a benchmark where utilities are just generated at random. A natural one to look at, especially from a political science point of view, would be a spatial model, where we've already saw that in the first lecture, I think. Where candidates and voters are placed on a 2-dimensional grid, and your utility for a candidate is the negative of how far away you are from that particular candidate. And then we also looked at a Mallows model. So we generate a linear profile using a Mallows model, and then for each possible ranking, we generated a random utility that represented that ranking. Okay, so we had 3 ways of generating utility models. Okay, and so we thought of this really as kind of a classification problem. So what you would do is we would have this stage of labeling. So you label the sort of optimal response you might get given that limited information. So you could in principle calculate that. That's really quite time consuming, but you can actually do that. And then we trained a bunch of multi-layer perceptrons to try to learn this particular labeling. And then we wanted to evaluate how well they did. So this is just some of the details about it. And then eventually, in just the usual machine learning sort of setup, we wanted to evaluate how well these different neural nets solve the problem. Okay, all right, so in a picture, this is what the data that we actually got. So along the x-axis here, we looked at different neural nets and sort of with different layers, and it's roughly going from the least complex to the most complex, right? And here, what I'm showing you is the plurality rule. Whoever gets the most first place votes is the winner, and Borda, which is well known to be quote unquote highly manipulative. Okay, and you can see here that under that when you have the right amount of information, so for plurality scores, the neural nets can roughly learn how to manipulate the election, even sort of with relatively small neural nets. Okay, as you change the underlying probability models, the level of profitability goes up and down, but the qualitative facts remain roughly the same. Okay. What I think is more interesting maybe is this graph right here, where what we do is we look at the average profitability over all the possible neural nets. So we just look over all of them and all the possible numbers of candidates we looked at, which is 3 through 6 and 4, 5, 10, 11, and 20 and 21 voters. So we kind of averaged over all of our data. And you can see that Borda overall is generally more manipulable. So the black line there is the ideal manipulator. So you can calculate what the ideal manipulator might be able to perform. And the neural nets can sort of roughly, and of course, it's going to depend on the type of information you get. But what's interesting here is Borda, you basically can learn to manipulate no matter what limited information you get. Not well as in other cases, but generally you can learn to manipulate. Okay, and you can see mini-max, this is a Condorcet system, split cycle and stable voting. Those are all Condorcet systems. You may not know what they actually are, but those are, it's interesting to look that those are generally less manipulable under this way of measuring manipulability than say Borda and even, well, instant runoff. I guess it's a little debatable about that. Okay, and again, the qualitative results that we're giving doesn't change very much when you change the underlying probability model. But generally, when you're in a spatial 2-dim model, the preferences are better behaved, and you might expect that there's not as much manipulation possible in that case, and that's what you actually get. And mallows is sort of roughly in between the spatial 2dim and the random utility. You would expect that there's lots of cases to manipulate in the random utility model, but with spatial 2dim, you would not expect there to be a lot, and that's roughly what we see. Okay, so in the interest of time, I'm just going to skip over that. So here's my conclusion. It's possible for MLPs to learn to manipulate preferential voting methods on the basis of limited information, but it varies significantly between the different types of voting methods. So roughly, there's different types of voting methods. So we have highly manipulable voting methods, even under limited information. This is Borda. This is very consistent with what voting theorists say about Borda, so this is sort of well known. Instant runoff, it's a little bit less clear how easy or not it is to manipulate instant runoff. We think that this shows that instant runoff is actually somewhat easy to learn to manipulate. And then there are some voting methods that seem to be highly resistant to learning how to manipulate, even when you have slightly more complex neural nets or MLPs. Okay, so additional questions. What happens if we allow a coalition of voters to manipulate rather than a single voter? Here we were just thinking about a single voter manipulating. And then, of course, this is making a strong idealization. I'm manipulating, assuming nobody else is actually going to manipulate. But of course, what you want to do is you want to learn in the context of other people possibly manipulating. And then finally, I think this is a very interesting question. What actually is the social cost or benefit of allowing people to manipulate? Some voting methods, which are just horrible, like plurality, it might actually be better if people actually were allowed to manipulate or did actually manipulate. You might end up with an outcome that is actually better. Okay. All right. Well, that's all I have to say. Thank you very much.